Hey, good afternoon, everybody. Hope you can hear me loud and clear. Uh, Joining us this Tuesday afternoon. Um, I've had a quick look outside, actually. It's azure blue in Costa del Halifax, and it'd be lovely to, in the chat box, let me know where you are joining from today. If you are at a secondary school, if you are just Key Stage 3, if you teach GCSE, let us know if you do that, or maybe you may be joining us from a further education college, and it'd be lovely to hear where you are joining us from today. Whilst people are joining the session, you may notice that there is a starter activity on the screen. Hopefully, you can see that nice and clearly. That says, convince me that x plus 3 all squared subtract 4 is equivalent to x plus 5 multiplied by x plus 1. And you're just asked how many different ways can you do it. So let me give you a few minutes to have a bit of a think there, and I can then meet and greet people as they are speaking to me in the chat box. So we've got Lindsay, hi Kaja, joining from Qatar. Fantastic. Hopefully it's not too late at night for you, Kaja, but wonderful to have you join us today. Um, Molly, Key Stage 3 lead for maths at secondary school. Wonderful. Stuart there joining from Essex. From South Wales, Natalie's joining us from here. 7 p.m. It's not too later than I thought there in Qatar, but it's lovely to have you join us. The Wingate School in Mexico City. Now that's the other end of the spectrum. So that's I wonder what the range is of the time zones of the delegates that we have so far. That's a maths question that we could explore. It's 10 a.m. where you are. That's wonderful. This is lovely. Thanks so much, everybody, for saying where you are from. It's wonderful to have such um, a lovely, engaging set of people here. Hopefully that you enjoy what we explore today in this session. So maybe give you a couple of minutes to have a little bit of a think about this starter. You don't necessarily have to do it in the chat box because it may be a bit complex to answer this in the chat box, but just to have a bit of a think about how you could convince me that x plus 3 all squared subtract 4 is equivalent to the product of x plus 5 and x plus 1. Wonderful. So we've got a really wide range of people joining us today from different provisions, looking at working with different students across either Key Stage 3 and Key Stage 4, or maybe in alternative provisions. Or pupil referral units I've seen mentioned in there too. So it's wonderful to have such a wide range of people in different teaching spheres there. Okay, so giving you a little bit of time to have a bit of a think in regard to this starter problem. And I think it's, oh, Matt, you've really, you know, well, it's 4 o'clock here. In Qatar, it's 7 o'clock. So you might be thinking it's too late in the day to be having a look at something like this in some complex. I'll put in brackets there. Algebra to start looking at equivalents with, but actually, it it may appear that this is Matt's only looking at higher tier year 10, year 11 type things. But actually, if we do this really well, there's no reason why actually we can support students to appreciate this from as early in secondary learning as year 7. And that's not to say that every single student in year 7 start looking at this in particular, but it depends on how it's explored. So let me just give you a couple of ways in which you could have explored how this is true. So one way you might be thinking, or maybe a student could think, is that you could use substitution. But if you actually only use substitution, such as that x is equal to 2, and substitute into the left-hand side and the right-hand side, yeah, it shows that both of those expressions in this identity are 21. However, it doesn't really convince us for all cases that this is true. Maybe, and probably I predict, the most popular way to approach this is to expand the brackets. So on the left-hand side, if we expand, we end up with an expression such as x squared plus 6x plus 5. And then we get the same on the right-hand side when we expand x plus 5 and x plus 1 together. Maybe you didn't spot that you could, the left-hand side is actually a difference of 2 squares. If we actually have something in completed square form, such like this, not all completed square form cases, but x plus 3 all squared subtract 4, we actually have the first term, which is x plus 3 all squared, that's a square, and then 4 is also a square. So if we find the square roots of each of these, we can then use the difference of 2 squares to factorize each of these terms, and then this results in x plus 5 and x plus 1. So a little bit of a sneak peek of something different there. But ultimately, I am going to come back to this question at the very end and how we can explore this in a very non-abstract way, because as you can see, there's a lot of symbols, there's a lot of abstract notation on the screen there. And this isn't the only way, and certainly not the way I would encourage that students explore algebra. And hence, today we are looking at how do we master algebra progression from Key Stage 3 to Key Stage 4 GCSE. My name is Matt Ainscough. If you've not met me before, which I assume many of you haven't, I am a secondary maths teacher and have been for over 10 years. I've worked all the way from year 7 in Key Stage 3, all the way up to Key Stage 5, teaching all sorts of different attainment levels, top sets, lower sets, as well as foundation GCSE, higher GCSE, A-level maths and further maths as well. And my roles are as a secondary maths specialist and head of post 16 actually at White Rose Education. And ultimately, the reason why I've been asked to do this today is I was part of an authoring team working in conjunction with Collins, hence why this is a joint Collins and White Rose Education webinar alongside a fantastic team of authors. So I didn't write the whole textbook. I'm not going to take credit for that, but I did. I was part of the team that did that in particular. Okay, so the agenda for today is I'm going to briefly share about White Rose Maths and White Rose Maths approach at secondary, what we believe are really key fundamentals of having success and having depth of understanding too. And then probably the most crucial bit of today is that we look at how can content from Key Stage 3 build strong foundational knowledge for Key Stage 4 algebra. This allows us to then think about how, working in conjunction with Collins, how we can how this pedagogy is exhibited in the textbooks themselves that we have available, that we have written with Collins. And I'll talk briefly about the structure of those textbooks in particular. And there is going to be time at the very end of today for some question and answer. But as mentioned in the chat box there, if you do have any questions at any point, do flag them in the chat box. And at an appropriate time, I'm sure that I can hopefully answer those questions to the best of my ability. Okay. So about White Rose Maths, maybe you have heard about us before, maybe you haven't, but our ethos and what we are all about is a world-class education for everyone, everywhere. This is our global mission, not just in the UK. We work with a number of schools across the globe, and this is across lots of phases of learning. And the main thing is that we offer free detailed schemes of learning from nursery and reception, early years, all the way up to post 16. And that post 16 provision at the moment is specifically around further education colleges and GCSE resits. And this provides teachers with guidance and high quality exemplar questions and how to support fantastic lessons. And ultimately that it's there to help serve a mastery approach, which is research informed, and that we are implementing this across all teaching of mathematics. And approximately 80% of primary schools in the UK use White Rose Maths, and 50% of secondary schools use our schemes and resources. Which is a fantastic thing that we're incredibly proud of, but we want to obviously increase that. So if you want to find out more, please do get in touch. But let's go into more detail about those things. So because we have our free schemes of learning, we do have some premium content, and this is low cost and comprehensive. We are we are very, very affordable and value for money. And we want to make sure that we're providing teachers with everything that they need to teach outstanding maths lessons, such as teaching slides, worksheets, starters, videos that help with this kind of step. That the videos and the teaching slides came from when we went into lockdown, and we wanted to provide schools and students with home learning resources, and we kind of just built on that. Teachers loved them, and they wanted them to be there available all the time. We also wanted to make sure there are opportunities for fluency, reasoning, and problem solving in all of these outlets. As well as supporting GCSE exams with pre-exam workshops, so basing some of making some papers based on past papers and pre-release material, for example, as well as assessments and workbooks, as you can see in the picture there that a student is working through. And one of the things that we do on top of all of this is we do partner with experts such as Collins to ensure that we provide schools with the full solution of everything, of being able to support students and teachers deliver maths in a fantastic provision. So as you can see on the screen there, we've got the front cover samples of the Key Stage 3 textbooks, and the 4 on the right are our GCSE textbooks, and I'll talk a little bit more about those in just a moment. Oh, actually, more towards the end of things, so rather than just a moment, more towards the end. A little bit more about us is that we also not just offer resources and schemes of learning for teachers to follow and plan and deliver fantastic lessons, but we also really believe in teacher training and school development, and this is a vital component of having success in the classroom, and that we wanted to make sure that teachers felt supported to be able to deliver and understand the pedagogy behind the approaches that we use. So we provide face-to-face and online webinar training, as well as some pre-recorded and on-demand supplementary videos to be able to support, and that's part of our premium content, and also on a bespoke booking service that we can provide with whole schools, or as online events where individual teachers can sign up to be able to do things. At the moment, I just noticed in the chat box a question about diagnostic assessments. We currently don't offer those diagnostic assessments at this moment in time, but we do have we have 2 versions of an assessment that could be used as a diagnostic. So we have a version A and a version B of each block of learning that we have. And version A could be used as a baseline, and then version B could be used then to kind of assess understanding towards the end of learning of that particular block. So we have things like assessments that can be used in a diagnostic way, but not specific. Here's the diagnostic for year 7, because every class is different. Every class is have a different learning experience, etc. So we've not got those specific broad stroke diagnostic assessments available. The main thing about our curriculum in particular is broken down into small learning episodes. For example, this is a block in year 7 looking at equations, and we can see there that we've got not just collect like terms on its own, we've got a step before that about identifying like and unlike terms, and step 3 and 4 are broken down into looking at how would we solve equations that with just an addition and subtraction involved, and then with a multiplication and division. And then step 5 has that chance to mix those around rather than it's just plonked all together, and that's just one learning episode. And these learning episodes are not all 1 hour or 1 lesson worth in length. These can be combined, but we wanted to break down these key components, that it's a coherent narrative that the key learning can be broken into digestible chunks. Another really important thing that we incorporate into our approach, and in particular through all of our phases of learning, but in particular at secondary as well, is the concrete, pictorial and abstract approach. You may know this as the CPA approach. And essentially what that means is it's the use of physical objects that can be used in the classroom. So, for example, some multi-link cubes or some Dean's blocks you can see on the screen there. But that this doesn't replace the abstract, but it goes alongside to support and then is removed at the appropriate time. For example, those 4 red multi-link cubes, for example, could represent a variable. Maybe each one represents D. And then the 3 blue non-multi-link cubes maybe represent ones. So those 2 representations you can see on the screen there are both representing 4D plus 3, which in the abstract is represented like we do using our algebraic notation with a coefficient. And we've got 2 terms that make that expression. So this is our approach. We wanted to kind of build depth of understanding around what the algebra actually means. And this is going to be a very component of theme throughout the rest of our afternoon. So I just wanted to pose a quick question to you, actually. Have you ever used concrete manipulatives in the secondary classroom? And if yes, which ones? So let me just give you a minute, open up the chat box. And let me know. I just want to kind of gauge currently what people are using, and if you're not using anything, that's okay to say no as well. It's not a thing to say no about. It's just to kind of let's share what we're doing. That's lovely. I've got a few people so far saying about double-sided counters and algebra tiles, using those for directed number. We've also got multi-link cubes being used, number lines, lovely. Number lines often get overlooked as a very crucial and really helpful representation. I'm glad that one's been mentioned there. Oh, sorry, Salma, that you're going to have to dash off, but lovely to have you join us. I'm sure that the rest of the recording can be sent to you post our session today. Bead strings, yes. Dean's blocks, Numicon. So there's some excellent naming of these tools. Recently, geoboards. I love it. I am a fan of geoboards. Not everybody is, but they can be really, really useful. And again, dependent on what they are. We don't use them just for willy-nilly of everything. It has to have purpose and direction around it. And a couple of people have mentioned a couple of the ones that I kind of want to focus on today. And apologies if you currently use some of these already. I know that some people online today may not use these. So I will kind of just introduce these in a if you're not familiar to them, but also if you do use them, hopefully there's something that you can consider about. Actually, I've not thought about doing that in particular. That's a really helpful and useful tip. So the first thing in particular that I want to draw attention to today is the use of double-sided counters that have been mentioned. The versatility of these counters is really, really powerful. And somebody already kind of mentioned it, which is brilliant. I love to see that people are already getting some of the ideas that are being shared today, which is around how these can be really helpful to build some depth of understanding around directed number. So you can kind of see there that we have a key on the right-hand side of the screen, which says that the yellow counter represents +1 and the red counter represents -1. Now, hopefully you can see here, if I show this up on the screen, that it's not just a yellow counter both sides. It's yellow on one side and red on the other. And this is really, really important. So make sure that the counters that you use are two-colored. You may call them two-color counters. Sometimes not all two-color counters are yellow and red. Some are blue and green, some are red and blue. I had the experience of this when I was covering a lesson for a colleague of mine, and he said, "Oh, can you use some directed number, please? Can you look at using some counters with them, please?" Absolutely, can't wait. I had all these resources available, all of mine in yellow and red. What does he have? Blue and red. So it's always good to check which ones you've got. So really, the basis of starting with directed number with double-sided counters is to really build a good familiarization with how to represent numbers as a composition of positive and negative. So you can see on the screen here that we've actually got kind of just somebody feels like somebody just picked up a load of counters and just dropped them on the table. And what number could this represent? Well, if we're told that yellow is +1 and red is -1, maybe you can justify that the overall number represented here is +1. Maybe you do this by counting that there's 5 yellows and then there's 4 reds. And then if you think, well, 5 and add -4, oh, that's 1. Yeah, it works like that. But actually, that's, again, we've got a bit of curse of knowledge there that we know that 5 add -4 is +1. But what about if some students don't? But what we can establish is that every time we pair together a yellow and a red, that this represents 0. And this is the first thing to really, really implement if you are going to use double-sided counters for directed number, is this visual of 0 pairs, how you can use something to represent nothing, which sounds abstract, but it's really, really fundamental. So nicely here, we can remove the counters altogether that pair as zeros to show that this is +1. And I just want to share some of the ways in which I've done this in the classroom, how I've got students to really, really have a good understanding of 0 pairs before we start doing any adding and subtracting at all. And the first thing I do is, well, actually make sure the students have got some counters if you have actually got them there at all. And if not, you can actually still kind of do this. I've still kind of done it with you can actually still do this without counters. You by just having some like a whiteboard and yellows and reds on and doing it that way. But I think this is really, really, really powerful. And the first thing I kind of do is, oh, can you represent 3 to me, please? Okay, everybody in the class, can you represent the number 3? Right, let's represent the number 3. And you might think, well, that's not a very good question, Matt, because most people are just going to say this, right? Not completely, no, because what it does is it helps, because you're just starting this off, it helps make sure that they're using the correct side of the counters. Because even though there are 3 counters at the top there, they are not the right color. This doesn't represent +3, it represents -3. And there's always in my, I've worked with some really low attaining groups in 7, 8, and 9, and done this across all of them. There is always, in my experience, somebody that comes up with a unique answer. For example, like this, that they can represent 3, and I've not even introduced 0 pairs at this point. They've just, and I'm getting them to just, how do you know that that's +3? And they can, well, you know, every time you have a yellow and a red, it can't, they might use the word cancelling out, you know, and at this stage, we're just getting them familiar with what's taking place. And then we can explore, well, actually, how else can we represent +3? Well, maybe we could represent it with 5 yellows and 2 reds. And here we've got 2 0 pairs. So actually, there's loads of different ways to represent just one number as a mixture of positives and negatives. Another brilliant activity to do is to actually get your students to get a handful of counters each, and they simply give them a good shake and they drop them on the table. And all I want them to do is just say what number is represented on your table. They're all going to get different answers. But the thing I'm looking for as I'm going around the classrooms, I'm looking for, are they individually counting the yellows and then counting the reds, which isn't wrong, or are they actually pairing up the yellows and the reds? Because I really want to make sure that they do the yellows and the reds, because it's really powerful for the next learning that takes place. So this isn't just 5 minutes of learning, by the way. I know we're going through it quite quickly, and we take time, and there's activities that we can do to really establish what 0 pairs are. But essentially, that's kind of that activity. Just I thought I had an opportunity to share this on the screen, but I'll do it really simply. So a few counters, but give them a good shake and drop them down. Oh, that's turned out quite nicely, isn't it? You know, we've got -5 there, and even getting them to have them in a line. And then we might do it again. Have a quick go and give them a good shake. What are the chances we get older? It's like playing Yahtzee. Here we go. Right. So we've got immediately, because I'm very good at subitizing, I know that there's 3 yellows and 2 reds. However, what I can do is pair together the zero pairs, so I can see that this is 0, this is 0, this is +1. Lovely. And obviously a few more counters here would be really great. And there's some great activities to kind of build depth of understanding. So, you know, is it possible to have an odd number of counters and represent an even number? How can you show the number 5 using 17 counters? You can really have some depth of understanding here without it feeling like this is the only way to explore it. So hopefully that's kind of giving you a little bit of inspiration about how to kind of introduce these zero pairs before we start to actually look at directed number. And directed number, as we know, if it's not explored, it has the potential to breed a lot of misconceptions, doesn't it? So, you know, here, I'm looking at how do we actually build this calculation of -2 plus 5? Well, if we use the counters, we can do it like so. If we have our -2, this will look like so, 2 reds. And then if we add in +5 like this, and to do it in this way of lining them up, we can see we've started with -2, we've added 5. Well, here we have 2 zero pairs. So that means that if I remove them from the picture, we are not increasing or decreasing the overall value. So this is another 0 pair, it can be removed. This is +3, and this is therefore showing that -2 plus 5 is equal to 3. Somebody mentioned the use of a number line. I would also show how this is occurring on a number line, us starting at -2 and adding 5 to get our +3. But what about if we have something like this, -2 plus -5? Well, here's our -2, and it's very similar to what we had before, but this time, rather than adding in 5 yellows, we're adding in 5 reds. And you could start this on a second row if you'd like, but seeing as though it's all the same colour, I don't mind actually doing this all as one row. So we've added 4 there. If we add one more, there's our 1, 2, 1, 2, 3, 4, 5. So sure, this is -7, like so. And you might be thinking, Matt, hang on, can I just pause you there? This is a session about algebra. Why are we looking at directed number in so much detail? And the reason being is because some of you actually mentioned about using algebra tiles, for example, but double-sided counters and algebra tiles are very linked. On the left-hand side, you can see the double-sided counters pictures that we've just explored a little bit in detail there of +1 and -1. And the algebra tiles, they're very much the same in terms that we have a yellow one and a red one, but these are just unit squares now instead. And then we have our X tile, which again has a positive side and a negative side. So this same appreciation of how we use can we use something physical to actually explore directed number. Well, the same kind of questions like -2x plus 5x can be explored when we're looking at collecting like terms. So really, this building a picture of -2x plus 5x looks vaguely similar to the example we just looked at before. So we have 2 negative tiles, so that's -2x, so 2 reds, and if we add in 5 X tiles, we can see that we've got a mixture of red tiles and green tiles, and every time we have 1 red and 1 green together, this represents 0. So again, by removing the 0 pairs from the picture, we can show that this is equivalent to 3x. And what about taking it one step further? 5x subtract -2x. This may be where we all get caught out on that it kind of all falls apart here. Because if we follow the same structure of what we've just looked at, we had 5x. Well, 5x is just 5 green tiles, isn't it, Matt? Well, yeah, of course it is. Yeah, I'm not going to argue with that at all. However, this particular representation of 5x doesn't allow us to subtract any red tiles because we're trying to subtract -2x, which is if we wanted to do that physically, we want to have 2 red tiles to subtract. So do you remember earlier when we were looking at how we represent 3, and there's more than one way to do it? And basically, if we just keep adding a 0 pair in, it allows the picture to stay the same, but to look different and have more tiles involved. And that's essentially the same frame of thinking we want to do here. Could we add a 0 pair in here? How would it help? Well, it helps because now we start to have some red tiles involved in the expression. And if we add another 0 pairing, we have enough red tiles to subtract 2x from here. And really importantly, this picture is still representing 5x. But now, once we remove those 2 red tiles, we are now left with a different amount, which is 7x. Okay, so you've got this linking directed number and collecting like terms is really, really helpful. But it goes even further than that, actually. What about if we actually start to look at something like solving equations? So something like this. We've got our model, which is we've got our model and our calculation split side by side here. So I'm just going to use my visualizer and do this rather than clicking through a PowerPoint. I think it's a little bit easier to kind of see what's taking place. So this is the equation I'm trying to solve. 3x plus 5 is equal to 14. And the reason why I've chosen this, I could choose obviously lots of different ones, but I don't want the numbers to be too large because I'm trying to try and make a picture of this. And if we use something like 30x plus 50 is equal to 140, that's a lot of tiles to be making a picture of. And not only are your students going to get very frustrated, also I'm going to get very frustrated as well. So top tip is to, if you're going to use representations and tiles, be really careful about the examples you choose, because ultimately, if you want them to build them, they need to be buildable, and serve a purpose. So the first thing I need to do here is actually build 3x plus 5. And like I think most people, I do this, or at some point in my, I've kind of really tried to establish the left-hand side and the right-hand side of the equation. Maybe some of us do this, and I think it really helps with like lining your equal signs up, doesn't it? I think this is something that maybe you do and you advocate for in your lessons. But for the purpose of this is really helpful because I'm going to actually replicate this in my model as well, that we have a left-hand side and a right-hand side. And this helps us to really start unpicking what this equation is saying. 3x, well, I need to use these tiles, so I'm going to build that 3x like so. Oops, I need to make sure I use the correct side and it doesn't flip over. And then I'm going to use my ones. So I need 5 ones here. I need to make sure they're on the yellow side, like so. And on the right-hand side, I think I'll do this. I think I should have 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Absolutely wonderful. Okay, so we now have our equation. 3x plus 5 is equal to 14. And this is a really, really helpful thing to actually take the time to digest for students. That with the aim of trying to solve an equation is ultimately trying to work out what the value of the x tile is representing. Yeah, because it's not a variable anymore. It's an unknown. It has a fixed value because in an equation, only one value, or we have a limited value, number of values of x that actually make this equation be true. So, for example, we can say, well, can x be 10? If we substituted these as 10 each, then we'd have 10, 20, 30, and then 35. Is 35 equal to 14? No, it's not. So we can really try to show here what's occurring in the model. And then ultimately we want to isolate our x bar, our x terms here. So if I isolate them, that means I need to have none of these ones here. So I think the most traditional way of doing this is to remove our 5 counters like so. So if we do that, I'm going to remove 5 from here, and I need to do the exact same on this side too. 1, 2, 3, 4, 5. This will test my counting skills to make sure that there's the correct number afterwards. And here we can just check out. All we've got now is on the left-hand side, 3x. Okay. And on the right-hand side, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Lovely. And now if I want to work out the value of one of these tiles, I need to do some sharing across both sides. So I need to split the x's into 3. And then I need to split these tiles into 3 as well. And if I do that like so, I can see here really clearly that if I divide both sides into 3, that x is equal to 3. Okay, so it's showing each of those steps alongside each other. when I got this wrong, when I first started to, I always like to tell wrong stories where I got it wrong because it helps to pass on the message a bit more strongly. I completely negated this section when I first started doing this with my year 7 groups, and it was great. You really engaged with what was taking place here, but it didn't add any opportunities for retention. They weren't making sense. So when I gave them a worksheet set of questions, it didn't make any sense to them. So it's really important to have the model and the calculation side by side. Now, you may not have algebra tiles available and accessible with you today. And that's the case for quite a few teachers, really. However, there is opportunity online to use some really, really powerful digital tools. So you could, for example, use this site here. So I think in the chat box, I'm going to ask for a link to be put through for this site here, which is on our website, but it's our digital tools for algebra tiles. So you can hopefully see that we've got 3x plus 5 is equal to 14, and you can set the calculation up like so. You can drag items around. You can add in this split vertical bar in like I've done, or you can remove it if you'd like. So it adds that left-hand side, right-hand side feel about it too. You can duplicate counters if you like by clicking on a counter and top right here. It duplicates it, and if you want to get rid of it, you can put it in the bin. But it allows lots of things to take place there that allows a little bit of playing around and getting familiar with the algebra tiles if you're really not familiar with them. So I kind of want to take a little bit of a pause and allow you to explore this, or if you've got your own algebra tiles, that's fantastic. And I just want to give a really brief activity. Maybe just choose one of these equations, and obviously I know that you'll be able to solve them. Okay, so the aim of this game is not to tell me the answers in the chat box. I've done this many times, and I get some very keen teachers who want to tell me that they're fantastic at math. I know that you'll be able to solve them, okay? I'm more interested in practicing how do we set these up and solve them through the use of algebra tiles. Okay, so just maybe take one of them and think, and maybe even imagine what that may look like. For that, for the last one we did, it was 3 greens and 5 yellows on one side, and then it was 14 yellows on the right-hand side. How do we go about doing that? So let me just give you 2 or 3 minutes before we move on. Okay, it's really good to have a bit of a play around with this. Hopefully, like you see, there's a nice example with B, that the unknown is on the right-hand side. And the great thing about using these tiles is that, if we were stood around a whiteboard, and from my perspective, it was 6 and 3x plus 9, like that. From your side of things, it'll actually look like 3x plus 9 is equal to 6. So it really helps overcome that misconception for students around the unknown has to be on the left-hand side, or you have to approach solving it completely differently. And some of you may have thought a little bit around how to that last one. It's like how on earth do you do 7 subtract 2x is equal to 1? Well, I just want to kind of hopefully set that up and show you here. So if we have 7 subtract 2x is equal to 1, I'm going to just build that on my side of the camera here, and we've got our 7, like so. 1, 2, 3, 4, 5, 6, 7. And rather than obviously subtracting 2x, we might want to represent our negative 2x like so. We don't have I don't think we have a weighing scales function at this moment in time, unless it's part of our premium content. Let me, rather than say a definite answer about that, Emma, I'll have a quick look at the end of today and hopefully get back to you with a definitive answer, because we do have some premium digital tools that aren't accessible on that homepage. It's part of our premium subscription, but I'll double check for you. But great question. And on the right hand side, we have our +1. So you might be thinking, well, how on earth do we go about balancing this out? So traditionally, we know that we need to we need to maybe think about, you could say like subtract 7 if you want to. Yeah, we could subtract 7. There might be a little bit of an issue on the right hand side with that, because there isn't 7 ones. But what we can do is, and I kind of like to use a little bit of emotion here. I get students to if there's anything you don't like about this particular example, what is it? And it's usually 9.5 times out of 10. They say it's these 2 red tiles here, or it's that it's got a negative in front of that coefficient. So the thing to really think about here was, well, how can we make there be no negatives there? The way to do that is to add in our 2x. And if we do that, then this will make there be 0 x's on the left-hand side. But what we need to do is remember the consequence of that, and we need to keep the balance. We need to add our 2x to both sides, like we've done on the left-hand side of our in our calculation. So the result of that is that we now have 2 0 pairs. So these can now be removed. And now we have 7 is equal to 1 plus 2x. And we can now subtract each of those like that. And we get 6 is equal to 2x. So if we share each of these out like so, we'd now have that 6 is equal to 2x. But actually just looking at one of those rows, then we get that 3 is equal to x. And this is okay to leave our answer in this particular form, and then we can rewrite it as x equals 3 if we wish. But this is really helpful to get students familiar with how to deal with a negative coefficient, as well as how to deal with the unknown on the right-hand side. So it can be a really, really powerful thing to use algebra tiles, a mix of double-sided counters, and that fundamental thing around 0 pairs to approach this. So this is the reason why we're looking at this today, is that actually that really key learning around directed number has so much of an impact on their use for algebra later down the line. And in particular, even just looking at maybe something like a pair of linear simultaneous equations. The great thing here is if we have what we actually have, and what we try to get them to do is to eliminate one of the unknowns. And here we're actually looking at an abstract representation of a 0 pair. Sam's asked the question, what if the students get -6 is equal to -2x? Great, I like that. Well, that kind of leads me on to the next bit. If they do get that, so if they subtracted both, you could go the long-winded way around. So we could add 6 to the left-hand side and make 6 0 pairs, and add 6 to the right-hand side. So you get 0 is equal to -2x plus 6, and then you add your 2x, positive 2x to both sides, so it results with 2x is equal to +6. So you could do that winded way around, or you can have a look at what we do next, which might enlighten you. So I'll try and bring that a bit full circle, Sam, with my full response. So the other thing to kind of really plow on about here is, and I might just sound like this just sounds like we're looking at directed number for the whole time, but this has such a fundamental part of algebraic understanding is around negatives. And if we can really conquer that, then we're setting students up fantastically. So the next point I want to look at for today's session is that negative is the opposite of positive. And you might be thinking, well, yeah, of course it is. But what has that got to do with anything, and why is this worth mentioning? Well, it's worth mentioning because it's actually a powerful vocabulary tool here that actually makes sense of actually in many different representations. So, for example, on a number line, a horizontal number line, we've got our positive and our negative are going off in different directions. We also have this on a vertical number line too, which for representing negative numbers, I find is actually really, really helpful, especially when we're ordering and we're first looking at the +3 is greater than -3, even though maybe their representations look very, very similar. The vertical number line really helps with that ordering sense. But ultimately as well, the Cartesian plane is two number lines, just joined together at the origin, one horizontally and one vertically. So we're seeing that this negative is the opposite in work with coordinates, work with the work in the Cartesian plane. We also see it with enlargement. For example, when we're looking at negative enlargement, the scale factor is still having the same impact in terms of the proportional change of size of the shape, but where it's enlarged from is in the opposite direction. We also see it with vectors, these two vectors, A and -A, have the same magnitude, but their directions are completely opposite of each other. And the thing that I'm harping on about is because this has a brilliant way of bringing into the use of the double-sided counters too. If negative is the opposite of positive, that's exactly what these counters are doing. If I have the yellow side of the counters, and if I turn them over onto the opposite side, I now have the negative. So to kind of exemplify how powerful this is, if we have an array of two lots of 3, then what we have when we turn all of these counters over is 2 lots of -3. But the crucial thing here is this is 2 lots of the opposite of +3. Yeah, 2 lots of the opposite of 3. So that's the link that I'm trying to make here. And then actually, what about if we have our red counters and we turn all of those over? Well, you might think, well, it just goes back to what we had before. Well, actually, if we have our red counters and turn all of them over, this actually is the opposite of what we had before, which is the opposite of 2 lots of the opposite of 3. I know that's a mouthful. However, if we link the word negative is the opposite, then another way to say this is that it's -2 lots of -3. That can start to then make sense of how a negative multiplied by a negative is a positive. And what I'm not saying here, and from my experience, this is I tend not to be like giving students like loads and loads of counters to do loads of turning them on, turning them over, and etc. like this. But it really helps exemplify the point. And to add to this, there's, I'm a big believer that, and some sources will say that actually it's really overwhelming to look at multiple representations. I beg to differ from my experience, because I also look at how to explore this through basic multiplication too. And I think this is a really crucial part of how to support students with their algebraic understanding. So, for example, if we did 18 times by 17, I'll hold my hands up. I unashamedly love an area model or a grid method approach. I know it's not everybody's thing. I know it's not even for students, because at primary school they look at having to use the formal column method. But I'm a big believer and big fan of using the grid and an area approach. And the reason being is, it might seem like there's more work, but actually it's a great visualization. And the traditional partitioning of 18 times 17 is seen as follows. We go our 10 hour 7, our 10 hour 8, and multiplying each component together, and then finding the sum of these to get 306. What we often don't do with students, and I've done this with year 7 groups, and it's fascinating. It really, really unpicks some of their understanding around multiplication. What if we didn't use 10 and 7 as our partitioning? What if we used a different number? What if we used 15 instead? What about representing 18 times 17 as 15 and 2, 15 and 3? Really strange. Well, what we should know is that it should add up to make 306. And if we do each multiplication as is, then yeah, it shows and it justifies that this has to make 306. How fascinating. But what about taking this even further? What about if we did it as a partition of a positive and a negative? That 18 is represented by 20 and -2, and that 17 is represented by 20 and -3. Well, 20 squared will get 400, and 20 lots of -3 and 20 lots of -2 can be found to get -16, -40. And maybe the bottom right corner is where the student gets stuck. -2 times -3, I don't know what that is. Is it -6? Is it +6? I don't know. Well, if we look at the other models and show that if we add up the areas that we do know, this should add to make 306. And really nicely in this example, 400 subtract 60 subtract 40 is 300, which justifies again that -2 times -3 must be +6. So using the counters to show that negative is the opposite. Sam asked me a question before, -6 is equal to -2x. So if I had that equation on my whiteboard, I was like, well, what happens if we multiply all of these by 1? So it stays the same number, but we turn everything over. Yeah, and that's what occurs. If you multiply both the left-hand side and the right-hand side by -1, it changes the counters over so that we have +6 is equal to 2x. So that's another way in which we could get that. So it's a brilliant question, and it's something to really, really think about there. So as we enter into the last 10 minutes of today, I think you might be thinking, why is Matt started to look now at, he's done directed number, talking about turning counters over, and he's now looked at area pictures of 18 times 17. What is this leading to, and why is it important? Well, if we actually take the time to explore multiplication in this flexible way, maybe this can actually set students up for algebraic success. So let's take that last one of 20 and -3 and 20 and -2, which was representing 18 times 17. But what about if we showed that product, rather than it be 18 times 17, what about representing it like this? 20 subtract 2 multiplied by 20 subtract 3. And this time I'm not using the multiplication symbol, I'm using a pair of brackets. Because this starts to then bear some resemblance to some of the stuff that we know students really have to get a good understanding of. For example, expanding expanding x minus 2 and x minus 3. And with the use of algebra tiles, representing this, it shows the connection, it shows the link. That if we have our x times x, we get x squared. If we have our x times by -3, we get -3x, and x times -2, we get -2x. So those -40 and -60, those sections are always going to be negative in this particular example. And then it also really nicely shows our -2 times -3 is equal to +6. Okay. So hopefully that's hopefully I've kind of come full circle on why the zero pairs and exploring multiplicative structures and understanding negative is the opposite of positive is really, really helpful. Let me give you one more activity before we get in towards the end of today. I'd like you to choose 3 consecutive integers, please. So just think them or write them down. Be nice to yourself with the numbers you choose, because I'd like you to square the middle number, please. You can use a calculator if you wish. I would then like you to multiply together the smallest and the largest number. I would then like you to find the difference between your answers. Okay? And I bet you your answer is 1. Okay? So, and you can choose that across any. If you chose 4, 5, and 6, square your middle number, 25. Multiply your smallest, 4, by your largest number, 6. Find the difference, 25 and 24. The difference is always 1. How can this be really helpful? I've actually done this with year 7 groups, and it's been fascinating because they get like, it feels like this maths magic. And then when it's all started to go to pot is when I started to try and explain it with some algebra. But actually, what I was lacking of was a visual representation to make sense of the algebra. And this is what this can be really helpful for. So if we have a number, and maybe the only new bit of learning there is consecutive. So our number that we have, and let's say it's our x, and then the next number after that will be x plus 1. Next number after that will be x plus 2. And if we follow the rules, which is take the middle number and square it, that will be x plus 1 all squared. And that would look a little bit like this. We have our x squared plus 2x plus 1. And then if we have our smallest number and our largest number and finding the product of those, it'll look a little bit like this here. And you can see here that both of these pictures have an x squared, Both pictures have 2x. The only difference is 1. So it's really, really nicely, and whether we show all of this with a year 7 group or just do that really nice activity to begin with, or maybe we do this later down the line, having these visual representations to show and justify these things can be really helpful. And these types of questions are not just for higher end year 11 groups. This can be brilliant ways to do some problem solving and investigative work with students at all attainment levels. It's really, really, really nice. But ultimately, these particular representations are helpful for a number of different things. For example, difference of 2 squares is really, really helpful. So if we have x squared subtract 4 and just built these as it looks a little bit like this. But if we've explored the structures of multiplication, that we kind of want this to look a little bit like a rectangle and needs to be filled in. Well, by adding in 2 0 pairs, we can complete a rectangle. Actually, it looks like a complete square, actually, doesn't it? And then working back from there, we can show that the factors here are x minus 2 and x plus 2. So really, really justifying the use of 0 pairs again. So it all comes back down to that directed number understanding to be really helpful. And then lastly, the starter activity that I gave you before. Do you remember? We had x plus 3 all squared subtract 4 is equivalent to x plus 5, x plus 1. What about if we actually didn't do any abstract, writing down here and actually just had our algebra tiles? We can build it. X plus 3 all squared looks a little bit like this. Here's our subtract 4. So I noticed that there are 4 0 pairs. So if I remove the 0 pairs from the picture and rearrange the tiles, we can rearrange it to look like x plus 1 and x plus 5. So it really, really nicely exemplifies that. So this CPA approach is really, really helpful for fantastic working from Key Stage 3 to Key Stage 4. And the key points I'd like to really to take away from today are really develop that students to have that really strong grasp of directed number, including 0 pairs, and those multiplication structures in order to understand those abstract algebraic concepts at a deeper level, because it does get really, really abstract, the algebra. And if we don't have those fundamentals in place, even if we bring in maybe some representations a little bit later down the line, it might not be a solid foundation enough for students to have success using a CPA approach. So the last little bit of today, so just wanted to kind of talk a little bit around the structure of the Collins textbooks and kind of how they follow this our pedagogical approach. So with Key Stage 3, if you're not familiar with these textbooks, these follow the same White Rose scheme of learning order. So all in the right way, all color coded with algebra or number, or whether it's geometric or probability, and it's broken up into sections like are you ready, assessing prerequisite knowledge, use of models and representations. So you can see that bottom right there in that Key Stage 3 block, looking at detailed examples, giving plenty of opportunities for practice, as well as stretching by asking what do you think sections to really give opportunity for depth of understanding there. At the end of each little chapter, there is opportunity for consolidation, stretch, and reflect, and end of block reviews. So very, very comprehensive way of using these. It's really does cover a lot of bases. The structure of the Key Stage 4 ones is very, very similar. However, we have 2 sets of books available for foundation and for higher. So book 1 in both covers number, algebra, ratio, proportion, and rates of change. And in the second book, it covers geometry, probability, and statistics. It's for EdXL and AQA versions. That's what's released at this moment in time. I think there's an opportunity in the there's a question in the chat box around Key Stage 4 textbooks for OCR. But the Key Stage 4 ones are on contents ordered by the actual topics. And what we then have is opportunities for exam practice as well. So you'll see there the little light green, blue ones are exam practices for that block. And then there is like an exam practice for that whole block on number by the red dot. Same thing of Key Stage 3. Are you ready? Prerequisites. Free text where models are exemplified. and examples that go step by step with some commentary around what those are to really support students on, and maybe even with teachers delivering. There's also a really great use of the calculator section here. That's option. It's an optional section, so it really helps to kind of, how do we use the calculator for this particular step? And it's flexible alongside that, because you'll see some questions have the calculator symbol by the side, and some said don't use the calculator, and somewhere they don't have either by the side. That means that either could be used in this, and so it's got that flexible approach. Also, the what do you think sections there, still highlighting the misconceptions and unusual examples, for instance. And we do have end of block exam practice in each of these, as mentioned before. It's linked to each strand and graded questions. So it gives you that these questions here are 1 to 3, and these questions here are 3 to 5. And really, lastly, the last thing I want to kind of say before I take some questions is that all of the examples that I've looked at with you today are use this predict CPA approach and have these available. So really do think actually there's something to take away from here, and the use of these textbooks actually allows us to do that. So the use of double-sided counters with directed number in the foundation block for number. We've then got foundation and higher examples of factorizing and expanding. Really helpful in either of the example or the free text. Even with linear equations, we don't just look at algebra tiles and double-sided counters, but bar models and other representations are used throughout, as well as for some quite complex maths, such as completing the square and even linear simultaneous equations. So you can see there's a little bar model there on the right-hand side. So I just want to say, as it's 5 o'clock now, a big thank you for coming along to today's session. If you do have any questions, do put them in the chat box, and myself or Collins will try to answer as best as we possibly can, depending on who's the best person to answer. But thank you so much. Where can we access tiles? There are many different places you can access these. You can get them through, I think YPO now sell them, TTS sell tiles. We don't actually sell the tiles or produce them, but there's plenty of places online that do. I think even Amazon have tiles available that you can purchase, but the digital tools that we have is brilliant as a great kind of in between there. But thank you so much for coming along. I can see some nice thank yous from people there. I hope it's been useful. I know I won't be able to cover everything in an hour, but I really hope I've given you something to think about and take away from today. And do stick around to ask any questions if there are anything that we haven't covered there. But thank you so much for coming along, and have a great rest of the week.